All right, let's dive into the invisible world of heat transfer. We're going to talk about how gases trap and move energy around, and it's a process that's absolutely fundamental, not just for some of our most powerful technologies, but for the climate of our own planet.
So here's a question for you. What could possibly connect the fiery, controlled chaos of a rocket engine with the air we breathe every single day? It sounds like a riddle, right? But the answer is all about how gases in both of these systems handle massive amounts of heat. And understanding that connection, it's surprisingly important.
And when I say important, I mean the stakes are incredibly high. This isn't just some abstract science problem. The very principles we're about to unpack are at the core of designing rocket engines. They're crucial for trying to contain nuclear fusion, for running massive industrial furnaces, and, yep, for accurately modeling our entire planet's climate. Okay, so what's the key to this whole mystery? What's the secret player? Well, it's a concept engineers call a participating medium. You see, a vacuum just lets heat pass right on through. But a participating medium, it gets involved. It's an active player in the game.
So what is a participating medium? It's basically any gas that doesn't just sit on the sidelines. It actively interacts with thermal radiation. Think of it like a crowd at a concert. It's absorbing the energy, it's creating its own energy, and it's bouncing that energy all over the place. This interaction happens in three main ways: absorption, emission, and scattering.
First up, you've got absorption. Imagine heat radiation trying to get from point A to point B through a gas. Absorption is like a toll booth. The gas molecules literally reach out, grab some of that energy, and keep it, converting it into their own heat. So whatever energy comes out the other side is less than what went in. But here's the thing, the gas isn't just taking energy, it's also giving it off. That's emission. Any gas that's warmer than absolute zero is constantly putting out its own thermal radiation. So it's not just a toll booth, it's also like a little radiator glowing with its own invisible heat.
And finally, we have scattering. This is where things get really messy. The radiation isn't absorbed, it just gets knocked off course. Think of it like a pinball machine. The energy comes in, hits a gas molecule, and just bounces off in some random new direction. You can imagine how this makes trying to track the path of heat, well, pretty much a nightmare. So you've got this cloud of gas, and at every single point inside it, you have energy being absorbed, energy being emitted, and energy being scattered in every direction, all at the same time. Trying to calculate the final results of all that chaos, that is a monumental challenge. It leads us to a master equation that, for all practical purposes, can feel totally unsolvable.
Let me put it this way. Figuring out how heat radiates from a simple solid wall is, it's doable. But with a gas, the heat isn't coming from a surface, it's coming from every single point inside the entire volume. Plus, the gas's properties can change based on where you are, what the temperature is, and even the wavelength of the energy. The mathematical complexity just explodes.
And this is what that explosion looks like. This is the radiative transfer equation, or RTE. Now, don't worry, we are not going to solve this thing, just look at it. You've got derivatives, you've got integrals. This is the master code that describes everything we just talked about, and it is an absolute mathematical beast.
And hey, don't just take my word for it. The source material puts it pretty bluntly. This becomes an integral differential equation, which is a really fancy way of saying it's a monster. The math itself tells us just how difficult this whole field is. So, how does anyone ever get anything done?
Well, here's the brilliant part. Engineers tame the beast. They don't try to solve that perfect, monstrous equation every time. Instead, they've come up with these incredibly clever shortcuts, a series of simplifications that get them answers that are good enough to build rockets and run furnaces in the real world. It's kind of a three-step trick. First, they just pretend the gas is gray. That's an assumption that its properties are the same for all wavelengths of energy, which simplifies things a lot. Second, they calculate something called optical depth, basically how foggy the gas is. And third, they figure out the mean beam length, which turns a complex shape into one simple average distance. Let's talk about optical depth for a sec. It's really just a way to put a number on how opaque a gas is to radiation. If you have a high optical depth, the gas is optically thick. It's like a really dense fog. Not much radiation is getting through. A low optical depth, that's more like a clear day. It gives us a concrete value to work with. And the mean beam length? This one is just
Genius. Instead of trying to calculate the path of every single ray of energy bouncing around inside a crazy shape like a furnace, engineers just calculate one single average path length. This trick lets them treat a super complex volume with one simple number. It's an incredibly powerful tool.
So, with these clever tools in our back pocket, the Cray gas idea, optical depth, mean beam length, we can actually start to model the real world. We can finally connect all these abstract concepts back to the furnaces and atmospheres we started with.
Okay, let's look at a classic problem. You've got a hot gas trapped between two walls. The hot wall is at 1500 Kelvin. The cold wall is at 900 Kelvin. And the gas in between, our participating medium, is at 1200 Kelvin. Using our simplified methods, we can now figure out where the energy is actually going. And here's what the math spits out. Turns out, the gas itself is absorbing a net 19 kilowatts of energy for every square meter every single second. What does that mean? It means the gas isn't just a passive bystander letting heat pass through. It's an active participant. And in this case, it's actually heating up. Now, let's take that furnace and scale it up to the size of a planet. Because our atmosphere works in pretty much the same way. Key participating gases like carbon dioxide and water vapor are mostly transparent to the high-energy light coming in from the superhot sun, but they are really good at absorbing the lower-energy infrared heat that the cooler Earth is trying to radiate back out to space. This imbalance traps energy and warms the planet. It's the exact same physics.
And this chart shows you exactly why. Unlike our simple gray gas model, real atmospheric gases are very picky. They absorb energy like crazy at some wavelengths and not at all at others. And look at that huge absorption spike for carbon dioxide right in the infrared range. That's precisely where the Earth is trying to shed its heat. It's like putting up a barrier at exactly the wrong place for heat trying to escape. So when it comes down to it, a gas is never just empty space. It's an active, complex player in the journey of heat. It's absorbing, it's emitting, it's scattering energy in ways that are mathematically mind-boggling. Now, we've seen how clever engineering models can tame that beast to get practical answers for something like a furnace, which leaves us with the big question. What will it take to perfectly model the dynamic, non-gray, and unbelievably complex mix of gases that makes up the climate of our entire world? Well, that remains one of the greatest scientific challenges of our time. Thanks for digging into this with me.